Okay, everybody, I guess we'll start up again after our short break. And our close friend and collaborator, Eric Wolf, will talk to you about our radiation scheme. So, Eric, you want me to share the slides or do you want to do it?
You can share the slides. I think I'll just, I only have a few slides. So
Okay,
go right ahead. I'll just yell, yell next slide.
no worries.
So,
Take it away.
all right. So thanks, Mike, for the kind introduction. My name is Eric Wolf. I work with the Radiative Transfer Code here with ROCKE-3D. The radiative transfer component of ROCKE-3D is actually a separate independent model called Socrates, which you can see is a long backronym. The suite of community radiative transfer codes based on Edwards and Slingo. Socrates originates from the UK Met Office, and a previous worker with the ROCKE-3D team, David Amundsen, he ported Socrates into ROCKE-3D several years ago. Next slide, please. So the first just general overview of, well, what is radiative transfer? For some of you, this is going to be a review. For others of you, this may be illuminating, hopefully more illuminating than review. So radiative transfer is the transfer of electromagnetic energy through a medium, this medium being the atmosphere. And it's a very simple statement, but the atmosphere is a very complex place. You have different absorbing gases in the atmosphere, you have clouds, you have different surface properties, you have the incoming stellar radiation, which is scattered back by the atmosphere, Rayleigh scattering, scattered back by clouds, reflected by the surface, absorbed by gases in the intermediary in the atmosphere. And then you also have your thermal stream, the radiation emitted by the planet, the black body radiation emitted by the planet, which is also absorbed by other gases in the atmosphere through the greenhouse effect, absorbed by clouds in the atmosphere. And the radiative transfer in large part determines the energy balance of the planet. And this balance of the radiative transfer energy, it can be very different compared to other planets. So as we've made our way through this tutorial, I think a theme that I may be so bold to say is many components of a 3D climate system model do not need to be fundamentally changed to model extrasolar planets, where you're often just talking about changing boundary conditions, changing things like the size of the planet, the rotation rate of the planet, the year, the length of the year, the surface compositions, things like these. These are boundary conditions. The dynamical core is based on fundamental physics. When we're thinking about atmospheres with water vapor in them, that is, yes, specific to habitable zone planets, but also still difficult, but fundamental physics about how water vapor can condense and interact in the atmosphere. Surface processes, again, if we change from Mars to the Earth to the Moon to Titan, the fundamentals aren't changing. We're just changing the boundary conditions of how exactly we're specifying the surfaces. However, radiative transfer is the one piece where you really have to make sure you're changing it correctly between planets, because the changes in the atmospheric composition between worlds will have a massive effect on your results. So most Earth system, perhaps all Earth system GCMs and ROCKE-3D, similar to many of the other exoplanet GCMs out there, you start with the core being the Earth GCM side of the house. And typically the radiative transfer schemes for Earth GCMs thinking about climate change are very tailored to that problem of, it'll do you well from pre-industrial Earth, from 285 ppm of CO2 up to a few doublings of CO2. But if you really want to start getting into planetary modeling and thinking about, well, a pure CO2 atmosphere on Mars, or a Titan-like atmosphere with a few percent methane, these Earth-centric radiative transfer schemes will undoubtedly give you poor results. Thus, Socrates was ported into ROCKE-3D because Socrates has a very unique, well, I shouldn't say unique, but it has very flexible flexible and durable capabilities in order to model a wide variety of planets that we do with ROCKE-3D. So next slide, please. So this is, I touched on some of these points, but this gives you a little bit more information of thinking about the different gases that we think about for terrestrial planet atmospheres. You have your downwelling solar radiation stream on the red, under the red curve, and then your upwelling thermal radiation scheme under the blue curves, and then you can see the different important gases and where they absorb in the atmosphere, or the transmittance through the atmosphere between water vapor and CO2 and oxygen and methane, nitrous oxide, Rayleigh scattering. We also have to think about clouds and aerosols, and they all have different spectral effects, different effects through the entire spectrum that have to be self-consistently and realistically incorporated. Now, radiative transfer is a very well-posed problem. There are many radiative transfer models out there. So that's why I backtrack to say that our capabilities aren't unique, because there are many different radiative transfer models out there. But the importance for a GCM is that you have something that is fast and that is flexible. So line-by-line radiative transfer models are the gold standard. And what they do is they'll calculate your flux through an atmosphere by going through every single spectral line, of which there are hundreds of thousands or millions of them to go through over a broadband spectra. However, this is much too slow for our 3D GCM. We have to boil down these millions of spectral lines for several important radiative gases per atmosphere that we're dealing with into a small number of manageable spectral bands. So typically we'll boil down millions of spectral lines into anywhere between 10 and 40 as order of magnitude numbers, spectral intervals for which we calculate the flux through to simulate with our GCM. And that using in that tens of spectral interval number allows our GCM to run fast enough with the radiative transfer. And as you've heard from other parts of the tutorial, still, if you're trying to run thousands of years with the GCM, it's a very computationally intensive process. And radiative transfer tends to be one of, if not the most expensive part of the model in a standard configuration. Now, when you start getting into adding aerosols and tracers, and that can be really expensive too. But in a standard configuration where you just have water vapor and clouds as your tracers, the radiative transfer is really the big one that's sucking up all the computational resources. So having it being fast, flexible, and accurate it's something people put a lot of time into, and that's how Socrates was born, in order to promote having a model that has all three of those components, both fast, flexible, and accurate. So next slide, please. So these are some important terms to think about, to remember when you're setting up your ROCKE-3D cases or reading through the material. So obviously Socrates, a radiative transfer model designed for use in 3D climate models, requirements being flexible, fast, and accurate. And these key terms are spectrophiles. That's a term that will come up very frequently. Chris Kolos will talk to us later today about setting up your planet and choosing the right spectrophile and where it goes in the run deck. So what is a spectrophile? So the way Socrates works, and this is both a strong asset, but it also can be a source of confusion, that Socrates there isn't just one master set of absorption coefficients in Socrates that you use for all cases. There are, and I'll in the next slide, I'll point to the file, our Google Doc file that lists all these. We have numerous different spectrophiles that have been tailored to specific use cases. So it's hard, it would be very hard, it would be challenging to make one spectrophile, one grid of absorption coefficients to rule them all. in the context of a GCM where we need to limit the number of spectral bands. So these spectrophiles are tailored sets of gas and aerosol absorption coefficients in cloud that we use in Socrates. They're set in the run deck under Spectrophile LW and Spectrophile SW. And I'll talk a little bit more about them on the next slide. We also have our stellar spectra, which is gives you the, well, I guess it's pretty self-evident, the spectrum of the incident stellar flux, which can change appreciably between assuming a solar-like star and a red dwarf star, or M dwarf star, which is very red. And in Socrates as well, this is another, an added layer with Socrates, that we have different spectrophiles have been created under one archetype of spectrophile, say a Mars spectrophile. You'll also have different stellar spectra within that subgroup, because Socrates takes an extra remapping step within its absorption coefficients, where within the spectral intervals, it'll remap the absorption coefficients weighted with the stellar spectrum in order to improve accuracy just a little bit. So when you're changing stellar spectra, you can't just change the stellar spectra, you also have to change choose the correct spectral file with that, which has the appended name of the stellar spectra as well. It's a straightforward process. And then of course you have your incident stellar flux, which is the total amount of stellar energy reaching the planet underscore S0. So next slide, please. So rather than repeat all this information here, this is actually my final slide. This is a short talk. I am pointing you to the links, and feel free to open them now. And I have a few extra minutes here. Let's give it 20 minutes to talk. So there's a little bit of time for Q&A. So here we have our user's guide. You can click on the Google Doc. It'll kind of walk you through the steps of how one sets up ROCKE-3D with Socrates, and where you set your spectrophiles and things like that, and how you make a new, if you wanted to personally, now I can help you do this as well. If you wanted to personally make a new stellar spectra, how would you do that, and things like that. And then the next one is probably the more important one, which is the list of spectrophiles. You can open the Google Doc, you can see we have a variety of them, between Earth-like cases, several Archean Earth cases where we're talking about elevated levels of CO2, elevated levels of methane. We have Mars-like cases and Paleo-Mars cases, which are CO2 dominated atmospheres. And then you can scroll through the list. And I think one thing that is important to note is I wrote a little kind of a word on selecting the appropriate spectral file that I'm gonna just repeat here. I think it is worthy of repeating that. So for some atmospheres, there's only one option given. So for Titan or an early moon atmosphere, other atmospheres, there's multiple different options. It might be confusing. There's multiple different Archean Earth cases. There's a couple different Mars, Paleo Mars cases that many of these, they overlap. So one thing I would say is don't overthink it. That there is some overlap between the files, and that's fine, and they've been tested, and where they overlap, the results converge. So don't overthink it. If you're like, oh, well, my case can use both, the AR or the AR10 bar, they're both appropriate. I don't know which one to use. Don't overthink it. They both work. Still, use the spectrophile which most closely matches your desired atmosphere, considering the main considerations are total pressure, and then the CO2 and CH4 limits are also maybe the presence of some trace species, H2, N2O. Now, these limiting terms that come in, you'll see in the spectrophiles, it'll say, well, this is good up to 1% CO2 or 10% CO2. That comes from the way that Socrates makes its, the way it boils down a line-by-line calculation into correlated K distributions for a GCM band model. It will tune as an automated step where it will tune the number of Gauss points required in each band based on an assumption for how much gas is in the atmosphere of a certain type. So you can really get fine tuning with Socrates and say, well, this spectrophile has 10% CO2 in its tuning value. Generally will say it's good for up to a certain amount and under. However, I've done a lot of testing. If you were to say take one of the spectrophiles that the Archean Earth one that's up to 1% CO2, if you were to accidentally run a case with 5% CO2, your error is going to be very small. It's not a huge difference. But where you do go really wrong is you really do not want to use an Archean file where it says up to 1% CO2 and assume it's a pure CO2 atmosphere for Mars. Then you'll start going quite wrong with errors up to tens of watts per meter squared. So I guess the moral of that is small violations in these guidelines, not a huge deal, but do not make some, gross difference and say, well, I'm going to use the Mars spectrophile and assume there's no CO2 in the atmosphere, or the Archean spectrophile and assume it's a pure CO2 atmosphere. So, if you have any questions, please just shoot me an email. The list of spectrophiles can be a little intimidating because there's a lot of them, but it's, don't overthink it. There's some overlap between the cases. Choose one that fits for you and you'll get good results. And then, on the final two, if you really want to start taking the next steps into Socrates, I provided here links to the Socrates technical manual, and then also the Socrates user's guide. So the user's guide will kind of really tell you how things are working when you're making spectrophiles, using spectrophiles, if you want to run offline cases, things like that. And then the technical manual gets into the radium transfer math. So that's my last slide. I think I actually managed to fill up all my time space with talking. So there's, I think, maybe a minute and a half for questions. And I know there's also will be around today for Q&A too. So thank you.
Thank you, Eric. That was great. One thing I thought I would mention quickly is, again, you can look at our previously run decks, and then there you can see the spectrophiles we used in specific cases. So you can see how they were motivated for those particular runs. So we have like a minute or two if anybody has a quick question for Eric.
Yeah, I have a question, but maybe the right question is whether I should email you rather than ask this now. So suppose that I want to make a change in my atmosphere. I don't know whether it's best to eliminate once. I don't know how the files work, so I don't know whether what you would recommend is that I want to make a change in a spectral line because I have either this new gas component or I want to imagine a change in a component, and I want to put that line somewhere else. Is it best to say, okay, I'll take down my methane or whatever, and then put this new gas species with its own coefficients?
So that's a great question. That's one that gets into more advanced usage of if we wanted to add a gas, for instance, that's not in, I think that's what you might be referring to. You want to add some gas that's not listed in the spectrophiles currently. It is a pretty
either that, or I want to make a change in the spectrum of a particular gas that is already there.
Okay, so like use a different line list, so to speak?
Yeah, right, for example.
Okay. So yes, it's a similar procedure as if you're adding a new gas or you're taking an existing gas and you want to use it with a different line list, the upgraded Hitran or whatnot. Email me about it. We're out of time here. It's a little bit more advanced, but it's totally doable within the Socrates framework. It's not that much of a deal. A little computational overhead, but it's a straightforward way to do it.
Great. Okay, I'll do that.
Great. So thanks again, Eric. We're out of time for this section. That was really great. And thanks for your question, Ricardo. So we're going to move on to Geronimo Villanueva, who is one of our colleagues at Goddard Space Flight Center, and Thomas Fauché. They're going to talk about planetary spectrum generator and how we use ROCKE-3D with that. So Geronimo and or Thomas, do you want me to advance these particular slides, or you want to share your own? It's up to you.
If you could, if you could advance the slides, Mike, that would be great.
Okay, then we go with that.
Okay, so well, hello everybody. So we're going to be talking with Thomas today about the PSG and the applicability to ROCKE-3D. So what we organized with Thomas is that I give a little intro about PSG, why we care, why we need it, and then Thomas we go into the details about how to run it. What we have a tool called Globes, and more what Globes does, and other details about Globes. So that's what we're doing. And so I just wanted to say both of us are NASA Goddard. Please, an idea of this talk is also to introduce us to you. Some of you know us, but also to, they are available to contact us and ask us questions. As you know, coding all these things, put all these packages together requires a lot of, involvement. So if you get stuck, please talk to us. We can certainly help. So let me go back to just start with this. Is that so? As Eric was talking about the value of radium transfer, and you all know that about it. I mean, you have a GCM, has a lot of components. Dynamical core. The radium transfer is essential to get the right energy balances, to know the temperatures, to know the structure of the atmosphere, and there are a lot of subtleties, as Eric was talking about. If you use correlated decay, line by line, and those make a massive impact on the energy balance of a planet. So they're wondering, now the question is, okay, I want to get a spectrum out of that. And you're thinking, well, I could just take the spectrum coming out from GCM. And you could. I mean, most of the cases, when you're looking at thermal emission, is so isotropic that directionality is not so relevant. But when you're doing a very peculiar, scattering calculations, then, all this, you're not so worried so much about the energy balance now. You're more worried about the spectral quality or accuracy of the spectrum. And therefore, then you need to do much more intensive radium transfer calculations. But you can do one thing. You can use ROCKE-3D with the sophisticated Socrates to give you the energy balance and the structure of the atmosphere. You run it for 1 billion years. You get the state of the atmosphere. Once you finish with that and you got the right state of the atmosphere, then you run you can run a very accurate scattering calculation as you will see the planet at that instant. And this is what we are proposing here, that you run your GCM that way, and then once you get the state of the GCM, then you put it into PSG, and PSG will give you a spectrum, and then it can also has, and I will tell you what PSG does. So Mike, can you go to the next slide? So what is PSG? So PSG is a radium transfer tool that has a web interface, and also you can actually install it in your own machine through a virtual container called Docker. But effectively, it's a radium transfer tool. That's what it is. And you may have heard about something called die sort. So effectively, PSG is die sort online, but it's a radium transfer calculator. Effectively, there as Eric was saying, there are different ones. So what PSG has been generalized to operate with multiple planets and atmospheres. And in order to do that, you need to kind of break the components of a radium transfer into subcomponents to make sure that they work in other planets. For example, give an example, we use something called the water continuum, which is something that has been studied over decades, and that has been tailored for Earth. If you want to apply that to a different planet, then you need to make sure that you transform it in the right way. So a lot of the generalizations that go into PSGs and make it adaptable to exoplanets or planets which are terrestrial in nature, but maybe they are a little bit different, and allows you to then therefore to model planets very different compositions. That's the thing about it. So in PSG, there are main things you set up when you make a simulation is the geometry. So there are 3 things you click there. You first set the planet you want to do and the star and how everything is being observed by you. You can say, okay, I'm in transit, I'm in direct imaging, I'm using a coronagraph. That's the first thing you do. Then you define the composition, and that thing comes from ROCKE-3D. So you take information about the profiles and how the atmosphere is structured. And then you said, okay, I'm going to be using that. I'm going to be using James Webb, and I want to know how much noise I'm going to get on this. And so it has different instrument modes you can plug in, and they will tell you the fluxes, but also tells you the noise. That's the other. Those are the 3 elements of PSG. So can we go next slide, Mike? So typically what you do is you go to that website, and Thomas will do a demo on how to run it. So the main thing about you need to, you know that well, but the thing about the PSG tool is that effectively you can generate a single one-dimensional spectrum. So you have an atmosphere, you assume the planet is homogeneous, which is obviously we know it's not, but you might the planet is homogeneous, you just run one spectrum and get one spectrum. So that you put generate in PSG, you will get a single spectrum. But as we are here today talking about a three-dimensional code, then you want to run a lot of those across the planet and then add them all up and then create a single spectrum. And that's for that we have an app called Globes, and now Thomas will talk about that. But the main idea about, I think my recommendation if you want to play with PSG is to first do a one-dimensional calculation. So you understand what goes inside into these codes. As every code or any computational thing, there's a learning curve for that. And we've been trying to make that learning curve as not as steep as possible, but at the end of the day, it's a Radium Transfer tool. So you need to have familiarize a little bit about what goes in, the geometry you're using, line list you're gonna be employing. So then it becomes a manageable thing. So my recommendation, if you want to do this, do a one-dimensional, get a flavor, about what the noises are, play with different instrument models, get a flavor what you're getting out. Once you get that understood, then you go to the Globes to do the full 3D stuff. So typically when you put generate, you get something like this. It does a graphical plots online too. So you can get the spectrum. This is a transit of a giant. And then you can see that you get the spectrum, which is the color dotted lines there. And then you also get the noise, which is the simulated noise there. So I give you an information about the spectral fluxes in transit for this case, and the noises. And so you see it's very fast. It did a full transit for James Webb in this case. It took only 2 seconds, 2.8 seconds, and it did the full ray tracing across the planet. So we go to the next slide, Mike. So what is effectively at the end of the day PSG? So PSG at the end of the day is a collection of a lot of modules of knowledge base we can create. So this Radium Transfer has been progressing for over decades. So what we did with PSG is to put all that knowledge from the community. A lot of the Radium Transfer knowledge actually comes from the earth sciences, and put it all together into this common package. And as I've been doing Radium Transfer for many years, one of the things that I learned is that there's always everybody has his own little code that is very difficult to run. Some people run it in Fortran, some people run in C, some people run in Python, and then there's always this language dichotomy. So what I want to do with that is to break that. So PSG is an online tool. You run it there. Then if you want to run it, you can run it again with an API, which is language agnostic. So you can use any language to communicate with it. That is to break some of these classical barriers for Radium Transfer. Still complex, but we've been trying to make that barrier a little bit less. So what goes inside? You have a line list. You can pick different line lists, Hytran, JPL, different, other non-LT line lists too. And it does, internally the PSG will pick if it has a big database of correlated K-tables that, as Eric was explaining, that they are necessary when you run a low resolution. But also you can do line by line. So depending on your requirement or your frequency range, your wavelength range and resolution, PSG will switch between the different regimes. And it has tables and line lists for different collision partners. So you can run an atmosphere in a hydrogen atmosphere, or in a CO2 atmosphere, or in a nitrogen or air atmosphere. You can also change the surface of the planet. So you can also say, okay, look, this planet is made of, I don't know, some rocks, or this is a Martian planet, or so you can also modify what we call the optical constants or parameterization of the surface and the modeling of the surface. So the boundary of the light transfer. So you provide that as a component too. You put the atmosphere at the line list. Then you have the atmospheric models. Again, you can plug in information, in the case from ROCKE-3D, from other GCMs too, and also from the database. You provide the straight structure of the atmosphere, pressure, temperatures, and abundances. And then it has these noise modules, which have been tuned for, been modeled to make things for ground-based. For example, something like you can model something like a VLT or keck. And it can also model things like from space, like James Webb or things like that. So that's what goes into PSG. So Mike, can you go to the next slide? So, sorry, I think you need to click it. Yeah. So what it does, what PSG does, it creates spectra. It can allow you to create spectra from 10 nanometers. Actually, you can actually go to the extreme ultraviolet, actually X-rays too, all the way to the radio. And it uses a mixture of different, modules, which are all in, for you, you don't have to worry about it. It's done, but internally it's done. It's picking different physics. Of course, every wavelength domain has a different domain, operation domain. So Psg will work on those domains, and it will give you spectra, from the photodissociation domains, from the UV all the way to thermal from the radium. Next slide. And one of the good things is valuable is that it has a full, every time you do a radial transfer calculation, or you want to see how the planet looks, you want to make, you need to know where you are and where the planet is and where the star is. So one of the key things that always been challenging is to know where I am, where the star is. So Psg has an orbital calculator for all exoplanets. So if you go, you put the planet, TRAPPIST 1e, you say right now, and it will tell you where the planet is around next to the star and the orbit. So it has a full 3D calculator, and that's very important, as I was telling, because for these particular calculations, when you want to see a spectrum from a planet, the geometry is essential to know where you are, because you want to calculate fluxes in the right direction. So Psg has copies the geometry, then gets the globe, and it knows where the sun is shining, where the things are, and it knows the angle for every point on the planet, and that is essential to get accurate spectra, especially when you work in the reflected sunlight, which is non-isotropic. Next slide, Mike. So as every calculation, you can do, as we say, in line by line, you can do correlated K. Psg will make the choices for you. I mean, it operates on, it knows that if doing a line by line for a huge wavelength range, it will take days. So obviously, it will use correlated K tables for those. But that's also multiple scattering. So you can add more sophistication into the scattering. You can add, what we call Legendre polynomials or n number of stream pairs. And that's a big requirement. And just to give you an example, if you want to run only one spectrum of Mars with high accuracy, looking in the optical, it will take 1 hour with die sort in a high accuracy. Of course, you have 10,000 columns and you want to run a simulation. You don't want to spend a year just to run one single spectrum. So one of the things what Psg does, it puts all together, is very fast, actually faster than die sort, and you can define the level of accuracy you want to do that to make it very fast. Actually, every typical calculation in Psg takes 2 seconds for a 1D thing, and if you run globes, it will tend, in a few seconds you can get a simulation. Next slide. And I think the good thing is that you can also have these are approximations to noise. They are not, they are not what we call ETCs or estimated time calculators of the missions, but they give you a ballpark how sensitive you are to this. So you say, hey, can I detect this molecule? And you can run it and say, okay, well, my error bar is going to be huge. Forget about it. So I give you an idea where you are. So of course, then my recommendation is always, if you want to do a full proposal for James Webb, then you go and use the ETCs. That has always been benchmarked. They're actually very comparable to what you get with Psg. But effectively, what the idea of this is that you get a noise information pretty quickly to guide you how far you are from your detectability of certain traces or abundances on the planet. Next slide. So these are the classical terms. Just for completeness, I wanted to say that these are the things that go inside of this. You see, there are the classical processes. So all the things are included there. I just wanted to say that the classical radial transfer has been accounted for. Yeah. The next slide, Mike. And one of the things that I like about Psg is that you have access to a full line list, and we add line lists all the time. And also surface components. We want to make sure that the full of line lists is a massive community. People are improving their line lists and doing a lot of lab measurements, and we try to collect that, and we try to collect from everywhere. So Hydron is a big source, but we also work with the ExoMol line list. We also work with the high energetic line list. We also work with the JPL line list. So we want to make sure that people can play with that, and you can actually choose and modify, run a simulation with one line list and see what happens, and then run with the other one. And you get a flavor, how every line list have some caveats. Hydron, of course, if you ask me, is tend to be very accurate, and even especially for temperate planets like ROCKE-3D tend to be, you're going to be fine with Hydron. But if you want to play with, you can also have access to other line lists. And there's a lot of pre-computed scattering models, so you can run clouds of different composition of water, ice, CO2 clouds, dust, and it has the misscattering and also T-matrix scattering codes. And what we've been working also lately is also improving a lot of the surface modeling. You can have, very sophisticated surface modeling if you want. You can add, also we added now recently glint and airshine and with the Cooks and Monk reflection models. Next slide. Okay, so I will tell you quickly about globes. Thomas will give you more details, but just to tell you a little bit about what it does, and then Thomas will tell you more. Can we go to the next slide? Yeah, so one of the things you do normally do, most of the people planetary scientists typically do, is they work in a 1D world. And what you do is you assume that the atmosphere is homogeneously. We know it's not, but this is what we've been doing for many years. But even if you assume the atmosphere is homogeneous, the incidence and emission angles are different as you see a planet in different phases. So one of the things you can also do, we develop an algorithm in PSG that even if you have a one-dimensional planet with the same atmosphere everywhere, the flux of the planet will look very different if you look at different phases, if you look at it for the night side or the day side, of course. No? So we had an algorithm that make that, it organized the disk into little sections, and it computes spectra in a fast way. Instead of computing 10,000 spectra, you will only compute 10 spectra, and it will be enough to give the same accuracy as a 10,000 spectra. So which is a big improvement, That's the idea of when you have an homogeneous planet. But of course we have a ROCKE-3D talk. So we go to the next slide. So the idea is that now we added recently, and this is something that it was actually something that Ravi Koparapu at Goddard was one of the people who encouraged this. Also Thomas was fundamental in this. And these are people who push me to add these capabilities to PSG, which are very important. And so what are these things that actually are intended for? So we're saying, we planetary scientists, we only do one simulation in the column. The idea of this is that, okay, let's do it right. Let's get the information from the GCMs at the last stage. When you have the final run, or the stage of the atmosphere you think is stable, you take the net CDF file, the state of the atmosphere, and then you start computing spectra with the right geometry at every single point. And that's what the globes does. It's an app, it's a component of PSG. So it runs PSG at every column. So that's what I was telling. First, familiarize how to run a single column. It's important what goes into that, and then go into the globes, which is, it can be a little bit, it's a learning curve. So it can be a little bit tricky. Next slide, Mike. So one of the things we added to globes, which is a neat thing, is that it has a nice visualizer of data, 3D data. One of the things that I work a lot with globe with PSG is to make it visually that you can see things quickly. You don't have to download files and make plots and some code. So the idea is that you can quickly see plots coming out. And one of the things we wanted to do with the 3D stem is the same, that you can graphically see that, first of all, is a validation thing. You upload a netCDF file into PSG, and you want to make sure that that file got uploaded right. You want to see, okay, my winds look fine, my temperatures look fine, my pressures look fine. So it will allow you to see, visually the movement of the winds and stuff, and it will allow you to see the fields at different layers. So it's very useful to check things and to make simulations that way. Next slide. So one of the things we've been working lately, and Thomas has been essential to make this happen, is to also with Mike Way, we've been working on scripts, which are what we do is the netCDFs can be huge. We're talking about gigabyte files. We want to make those files small. So we work with Thomas and others to make that accessible in a GitHub code. We transform those big files into a megabyte file that we upload into the server. Next slide. Yeah, so this Thomas will explain all this. And I think, well, Thomas, actually, if you wanna, maybe we stop with the slides, and Thomas, you wanna take the lead now on the thing, and you can even show,
sure.
And then we'll go into the details. Okay, thank you, everyone.
Yeah, okay.
Thank you, Geronimo.
Hi, everyone. Mike, can you stop the screen sharing? I'm going to actually share mine. Thanks.
Okay, go for it.
Okay, this one. Okay. All right. So thank you, Geronimo, for the great introduction on PSG. And so I'm going to do a short intro on globes, actually. And so when you are on the PSG main page, like here, how do you access to globes? So just have to go on here, application, and you have the globes planetary mapper. So here you can see what Geronimo was showing also in a slide. That's a very nice animation here of Earth, and you can really see the winds. And so that's a very the strength of globes, where you can really have a nice visualization of what you have in your GCM. And so again, the idea is to have your netcdf file from the GCM and actually to convert them into a binary file that PSG will be able to read to do the radiative transfer calculation. And for that, actually, globes take every atmospheric column in your file and does a 2D projection in an observational grid. And this 2D grid is then sent to PSG to do the radiative transfer calculation. But this, of course, will be great if you can do it at the full resolution of your GCM. But I mean, it's possible, but it may take maybe 1 hour or so to do this at the full resolution of the GCM. So if you want to do it at every phase angle, it can take a lot of time. And so Geronimo has included something which is very cool, is a spatial binning. Here, by default, we put 200, which means that actually you are going to take 200 longitude point and 200 latitude point, will create a box, and the property will be, atmospheric property will be aggregated in this box, and only one projection will be made in the 2D, and so you will do a radiative transfer calculation. It will be very coarse, of course, because you will average everything in this box, but it will be super fast. And so you should keep the 200 binning only for test to see if you have correctly ingested your netcdf file to globes, but you should never use 200 to do your real computation of spectra, because it's going to be very wrong. Instead, we recommend that you have a spatial binning of 3, which means that you're going to have 3 coordinates in longitude, 3 coordinates in latitude. So basically you have 9 points, and I pre-compute here what you will get here. And so all these white dots here will show you where the radiative transfer calculation will be made. And again, you have a box around them of 3 by 3 where you do calculation. And so here you can see the nice, so it's a simulation from Proxima Centauri B with the dynamic ocean that Mike provided to me. I think it's from Tony.
I don't think we see your, sorry, I don't think we see the screen.
I think I need, okay, I think I should have to change the screen I'm sharing. Hold on, good point. There we go. You see it now?
Yes, yes, we can see it now.
Okay, perfect. Okay, so this is really the spatial binning of 3, and so yeah, you receive that you have many points, and so there are many radiative transfer calculations that are made. But again, it will really take you few minutes to do that, and so if you do a lot of phase angle, it can take a little bit of time, but it's important to ensure the accuracy of the calculation. And you can see here the surface temperature you see, and you see the nice lobster pattern here due to the dynamic ocean. And after you can change what you want to show. You can change, you could put like the pressure, for instance. You can put the water content, a lot of things. But so now let's come back. I'm going to have to switch again the screen to get back where I was for Earth. There we go. And let's say that you want to include your own netcdf file. And so how can you do that? So you need to have more information. So just click here for more information, and that will teleport you in this page that explains briefly what globes is about. And what is very important is that in this second step here, you have a link to a GitHub repository that Geronimo has made that will contain the files, the Python file that will help you to convert your netcdf into a file that can be read by globes. So let's take a look to that here. And so you can see you have few of them. You have Atmos, which is not a GCM, but you have for SOCAM, LMD, you have Mera, you have ROCKE-3D, the Metofis model. And so you want to download, of course, ROCKE-3D, which is your favorite GCM. And you also want to download the phase.py Python file. This script actually is going to help you to run globes for different phase of angles, so you don't have to do it manually. So you will basically do a loop around the phase angle, so it's very convenient. So let's say you have downloaded these 2 files, and you put that in a directory. You may not see my directory right now, but let's see, I'm going probably to have to play many times with that, but it's not a big deal. So okay, so you put this GCM GCM ROCKE-3D.py file and your phase.py script in one single directory. Here I'm using Jupyter Notebook, so the extension is slightly different. Now let's take a look to your GCM ROCKE-3D.py file. Still, you're going to change the share screen. Well, here. Okay, so what this script does, again, is going to convert your netcdf file into a binary file that's going to be read by globs. These binary files will be created as GCM_PSG.dat. So what you need here, you need your ROCKE-3D AAJK file, your ROCKE-3D AAJL, and your ROCKE-3D AIJ file. Because this different ROCKE-3D output will contain different input for globs that are going to be important. In the first one, you have the winds, for instance, and AGL, you have everything related to the temperature and water and clouds, and the 2D AIJ is all about surface, albedo, and temperature. So, okay, let's do the conversion. And after you have many PSG parameters that here we put as default that you will need to change if you want to run your planet around a specific star. You really have to change the star temperature, the radius, and so on. But here we just put a default configuration. Again, if you have questions, just ask us, because here all the PSG parameters can be a little bit complicated to get first.
One small comment here. So as Thomas was explaining about all these parameters, and they look a little bit cryptic. So when Thomas, when you go to the website, there is a link that explains what each parameter is. And importantly, every time you see all that stuff, the upper part of PSG, all the upper part, this is all what the help documentation is. We're improving that. We're trying to make it much more. It's still a little bit sparse, but we want to make it more. But you will get a lot of information there about how to run things, and you may be able to see what the numbers are, what these numbers are. But there is a section in PSG in the remote operation of PSG that explains which of these numbers are.
Okay, so where I was, okay. Can you see? I'm trying to get back actually on my Google Chrome. There we go. Sorry.
See Jupyter Notebooks.
Yeah. Okay. Back to Chrome. So here, what I'm showing is the phase.py file that I said that it's important also to download. And I put this on Jupyter Notebook. And so basically what it does, again, is going to look at your folder when you have stored your ROCKE-3D AJK, AJL, and AIJ file. And here you have few input parameters that's going to be what phase angle do you want to start the simulation? Here 0, what phase angle do you want to stop? 360. The phase step, so I want to do it every 45 phase angle. The beginning of the simulation, again, here we put 200 for the test to go fast, but always use 3 or a little bit more than 3 if you want to have a compromise, but never above 50. The minimum wavelengths, 5 micron, the maximum wavelength, 18. This can be adjusted, of course. The resolving power, here I put 50. Again, I wanted to speed up the calculation. And what do you want in the term of unit here, a part per million, because I just want to have a relative measurement. And after, here, this PSG URL thing is basically what Geronimo was mentioning previously. That's going to help you to call the API that is going to call globs for you and do the relative transfer calculation. And so at this step here, it's simply calling the file I was showing you before, which convert your ROCKE-3D output into globs and create the famous GCM_PSG.dat binary file. And after this line here, a little bit complicated, is going to send this binary file to globs, and globs will do the calculation. Again, under you have few parameters here that are related to the instrument. How many frames do you want for your calculation, the exposure time per frame, the resolving power, and so on. We have a default here, but you will need to adjust that depending on which instrument also you want to simulate. And after the last part here is just doing a loop of the calculation around the phase angle that have been mentioned at the beginning of this script. And nicely at the end in compute here, you can see all the step in phase angle, and we'll plot a very quick plot here to show you the spectra that you have computed. And so it's also interesting that all of them has been saved in the Spectra directory that is created by default if you don't have it. And so I'm going to just go in this, and I will show you. Hold on. Share. Okay, so you're here, and you have created all these phase angle files, which are actually Psg outputs. Where is TextEdit? There we go. And so, yeah, you have the regular Psg output file. We have all these headers with many information. And after, you have your different columns with wavelengths at first, the total, which is what you are interesting about, is your spectrum. The noise, and the third column here is the stellar complete. Everything is put constant, so you don't really have to care about this one in this case. And here, Proxima Centauri B, which is in this situation, is virtually identical to the second column, so you can use either column. And so yeah, you can use your favorite plotting tool, and you can plot your spectra. And I want to finish to come back quickly on where is Chrome, because you can also do it. So as I said, you have created this GCM .dat binary file, and you can directly upload it on globs, so you can see all your simulation looks like directly. And so it will take a few seconds to upload. A little bit more.
Yeah,
it goes faster when
you didn't see because of the screen sharing, but so normally what he did, when you click at that, it will open a Finder window. You click your file, and then the file will now normally the files are small. These converted binary files, they tend to be less than 10 megabytes, 5 to 10 megabytes. And so you need to upload that to the server. This is because we do it with the PSG server. You can install PSG in your own local machine, and of course it's going to be instantaneous. But I mean, this, as Thomas was saying, this is because we're going to run it in the online version.
Yeah, I insist to take a little bit more time than also usually, maybe because of the share screen. And also I think when I am on a VPN, it goes faster, but here it's a little bit slow, but it's still loading. Yeah, I think normally it should be in, but I think, yeah, it's a bit slow with the share screen. But yeah, basically, so your file will be uploaded here, and you can still change few parameters here. You can change the phase angle. Here is by it's at 0. You can put 45, 90, anything you want. You can see the molecules that you have in your simulation and aerosols. You can click here and you can change them. Same here, it tells you about the instrument that you are this wavelength range and resolving power. You can also adapt that. And again, the spatial binning, which is the important parameter. But yeah, it's still
and Thomas, and if you where this says GCM data, it says upload GCM. So also just to familiarize to run that, so there are some pre-computed templates that you can also preload. They're on the server, so they're pretty fast to load. And again, these are good ways to to see, okay, this is what okay, so now got uploaded. So you see, they can also load on those templates. Yeah, go ahead, Thomas.
So actually, when I click on the menu, you don't see the menu at all.
Now we see. We didn't see the Finder. Yeah, now we see that. We see
okay. So yeah, what Geronimo was talking about is all this template here that you can load, and just to familiarize you with globs. And you can see here, so we see the winds. Here, what is a little bit weird is just like it's an interpolation. So when you remove the 2D interpolation, you see exactly what it is. So and so yeah, as I said, you have many parameters like previously. You can put again the surface temperature, and change as I said, the phase angle, and recompute the simulation, and yeah, and you can basically see all the spectra will be updated. It may take a little bit of. Oh, we go. It was fast. Okay, so here you have your spectra nicely computed there. And I think nice thing is when you, so here again, it's very coarse. You have only one point here because of the binning of 200. You see, if I quickly go back for the last thing to my high resolution one, here. So after you can basically click on different location on globes, and you can see how the spectrum looks like at this particular location. And you see here it's changing at the bottom. It's a little bit slow, I think, to actualize again. There we go. And you see that it changed a little bit from the total spectrum that you have in blue, and you have some particular location where you can see how the spectrum looks like. Of course, for an exoplanet, you're never going to resolve especially that, but it could be interesting if you do something with Venus, for instance. Yeah. I think it was everything I wanted to say. Do you want to add anything, Geronimo?
No, that's perfect. And again, you know, as you saw, there is a lot of, you know, it's a learning curve with everything. And the main idea for us is that what we did today with Thomas is to introduce you to the interface, so it's not so intimidating. And maybe you can try to see if you can run it yourself. But the most important thing is that contact us. I mean, we are open to, we want to make this much more available, and we are all the time learning and making improvements. So if you tell us that this is glitchy, or this we can also go and improve it. So yeah, guide us, and we can work on that.
Great, thank you, Geronimo and Thomas. That was fantastic. And remember, these videos are recorded, so if the clicking was a little fast for you, as it often is for me, being elderly, I feel these days, you can always go back and watch the video on YouTube, and you can see in detail what Thomas is doing. But as you've seen, PSG has tremendous amounts of functionality. These gentlemen have only touched less than 1%, I would say, of what this tool can do. It's incredibly flexible, incredibly useful. And you can get a lot of very interesting things out of your data from this. And Thomas and Geronimo have already published several papers using PSG with GCM data, which have made important contributions to the literature, I would say, for example, on the TRAPPIST system.
Thanks.
So if you all want to add, I could let you ask one or two questions before we take our lunch break, if anybody has any quick. Otherwise, we can wait until this afternoon. But if anybody has a quick question, please go ahead and ask it. Go ahead, Nick.
Could you guys generate the transmission rather than the emission spectrum? So the amount of light that is blocked?
Yes, so go ahead, Thomas, go ahead.
No, I was going to say, yeah, I think on gloves, you just have to select and put the phase angle of 180 degrees, and it will do basically the transmission spectrum. I can maybe do a very quick.
Now I'm confused because my understanding from what your presentation was that you always provide us the emission that comes from the planet, even if we are looking at the night side.
No, it's actually computing the spectra at the right geometry. So as Thomas was saying, is if you're the planet is in front of the star, then the PSG knows that you're in transit, and then it will give you the transit spectrum. And the transit spectrum is a combination of two things: the self-emission of the planet plus the light that's been blocked on the planet. And PSG will give you the two components, and then you can plot them independently. But it will give you the two. As you say here, you get the transit, which is the purple, and the apparent transit, which is the red one, which is the transit, which is the light lost by the planet, but also the self-emission of the planet that is self-emitting. So it gives you both.
Okay. All right. And if I want to go, sorry for the second question. And if I want to go to high resolution, I can have my high resolution spectrum of the star, I assume, and that will automatically be used.
So right now, so if you do transit spectra, if you do the spectrum which is in relative to the star, you just get the spectra in relative to the star and you multiply by your own stellar spectra. PSG has templates for stars. Some of them are very good. You may want to use them. Some of them are not so good. So you can choose. But yeah, effectively, you can compute out PSG outputs in flux units, in watts, whatever, or you can also plot them in relative quantities, like ppms relative to star. Then you can multiply by your own desired stellar spectrum.
Yeah. Okay. Thanks.
Great. Any other quick question before we take a break? Okay. Great. So I just want to thank again Geronimo and Tomas so much. This was the first go at actually doing the demo, and I think you guys did a fantastic job. So thank you so much, and also thanks to Eric earlier for his presentation. I think PSG and ROCKE-3D are going to do great things together. We have a few projects in mind already. Nick has projects in mind. I think we can do a lot of beautiful work.
Yes, and for us it's great because as we do this, we improve a lot. So that's why I mean this connection with ROCKE-3D is very important for us. So yeah, the more we do, the better. Yeah.
Absolutely. Okay, let's take a break then, and we'll hook up in an hour from now, and Chris Kalos will go us through how to make a planet, and we'll have a little more discussion in our Q&A. Okay.
Just real quick, I'll put in the chat. I'll put in the chat some files that I'll be using, and because I'll just basically be going through a run deck.
Great, thanks, Chris. Everybody, take a look in the chat during your break. See you soon.